our department outstanding graduating senior.
Oh yeah, and he's our department outstanding graduating senior because he's double wonderful.
You give me a lot to live up for this
That's
time.
right.
The display light is blinking. It should turn on in a second. But thank you, Randy. As he said, I'm Matt Treflick. For those of you who don't know me, I'm a senior math and computer science double major with a minor in accounting, and I'm graduating tomorrow. So it's pretty hard to believe. And then my topic for my senior project I chose was nonlinear dynamics in the A-star n plane, or the A-star n lattice, depending how you want to call it. And so this topic, we'll kind of go into it, but it's going to be a little bit different because there's a big portion of research that went into it. And I'm going to kind of skim over the research. I'm going to explain it as well as I can so you guys can understand what I was working on. But if you want to read more about it, I do have my paper up on Euclid, and you'll be able to get a little more in-depth study of what I was able to research. And then I'll move on to show you guys the GUI that I created that sits on top of this, all this research that I did, and give some examples of what to show and what I worked on. So we'll do a quick demo. So we'll move on. So the project goal simply was to create a GUI tool for modeling nonlinear dynamics in the A-star n lattice. This was a project that I worked on a little bit with John Sarkala. He kind of gave me some of the information about the A-star n lattice and nonlinear dynamics, and I kind of wanted to try to combine the two and see what I create with it, and I'll go into the reasons why we chose these specific areas. So going to the research, nonlinear dynamics. Nonlinear dynamics is a study of essentially modeling real life, creating models for real life. So, in real life, not everything's linear, not everything can be graphed by a specific function. So instead of having a function, you create a vector field. You can run trajectories, which you can see this T over here with the blue swirl, that would be a trajectory. That's, a ball rolling down into some sort of cylinder or some other thing like that. And then we can create a vector field around these trajectories. And you can add a bunch of trajectories to be able to model this vector field. Once you have the model, you can then add in your own trajectories, your own items that'll follow the vector field, and you can estimate and model what would happen in real life, if that makes sense to you guys. And so then if we look at B, what we have there in the red dot, that's an attractor. A good thing to think of an attractor, something I hadn't ever thought before, is it's a limit point of a state space. So the state space is the space at which we're running these simulations. We've chosen a specific area, we've chosen specific bounds, and we set the boundaries of the system, and that becomes our state space. And once we have the boundaries of the system and we have an attractor there, we notice that all the lines, all the trajectories will limit to that point, and then they can expand out afterwards. But the key point of a limit is if you bring it back the other direction, it should model the same way and end up going through that same limiting point. Another way to think of an attractor, that red dot, it would be a basin. So if we have a three-dimensional plane and it dips down in the middle and there's a low point, that can be thought of as like a basin. So it kind of follows that slide down into the basin. A repeller, or the opposite, which is a little bit demonstrated here, would be like a peak. That's something large in the middle. So this is kind of a really cool thing. This was when I was reading this paper, or book actually, one of the coolest things I found was we have an attractor and repeller vector field. So what happens there is you can see the trajectories going around. That red line, that over there is the attractor. It's actually a directional attractor, and it's pulling all the trajectories down into this loop. That red dot in the middle is a repeller, and it's repelling them outwards. So you notice we come in, we center on into the loop. Once we enter it, we then get repelled back out to the loop, and it continues. So it's going to be a continuous cycle within that state. So the nonlinear dynamics continues to go on. It goes into oscillations. It covers a lot more modeling, three-dimensional modeling, time spaces. I focused purely for this project on attractors and repellers because those were the systems that I was going to try to demonstrate through this hexagonal plane. Quickly, we'll go into Breitenberg vehicles. So in order to have something to navigate these trajectories, we had to have something to wrap around these attractors and repellers. I went with a type of automata known as a Breitenberg vehicle. And that's a really pixelated image. I apologize for that. So basically, for those who don't know, Breitenberg vehicle has in this case, has two simple motors and two simple sensors. The sensors at the top receive value from the light, and the stronger the value from that light source is, the stronger they can power the motors on their respective ends. So 2A in this example, because it's the right sensor is closer to the light source, and the right motor is being powered by that light source, it's going to start turning to the left, and it'll be repelled from the light. Opposite, though, we have 2B here, which, as a Breitenberg vehicle with the lines switched, the left sensor is going to pull it towards the light because it's going to power the right wheel, and vice versa. And then I originally titled it Cellular Automata in the A-star n plane, and then I realized, no, even though we're working with a plane of things, it wouldn't be the same combination, so I went with Automata of Breitenberg vehicles. So now we get into the really fun stuff and what I spend most of my time working on, which is the theory of permutahedron and then the tiling of this A-star and lattice. So a permutahedron, so I don't mess it up, it's a polytope of n factorial points that exist in the n minus one, or it's an n minus one dimensional polytope type that exists in the n dimension. And I know it's really complicated, so this is the best example. This is an order 2 permutahedron, which, that's actually an order 3 permutahedron because it's a 2-dimensional shape. You notice it's a 2-dimensional hexagon that bisects a 3-dimensional cube, and in this case it has side length of 2. So if you tile all of these and you adjust the camera or our viewpoint to be orthogonal to this plane that we've tiled it with, we get the A*3 lattice, if that makes sense. So the A*3 lattice can simply be thought of as a 2-dimensional tiling of a plane with hexagons, and I'm sure you've seen hexagon fields. Yes, Andy?
And you know that it's 1 dimension less than n because all the permutations all add up to the same constant.
Right.
So it must be a subset of the plane x plus y plus z equals 6, or x plus y plus z plus w equals 24, et cetera, et cetera.
Yep.
There, see, I'm paying attention.
No, that's a good point, yeah. And then, so going off of that example, then if we go down a level, that would be just a straight line because it would only have 2 vertices, and we go down, it's a single point. If we go up, then it'd be a 3-dimensional tiling of these permutahedron that make up, and I can't remember what the thing is.
Truncated octahedron.
Thank you. Truncated octahedron?
Yeah.
Okay, yep. And then those would tile to create the A*4 lattice, which is going to be a 3-dimensional lattice. And Andrew Schertz actually explored a bit of that, more 3-dimensional stuff in his talk last year. And his paper, or not his paper, the paper that he used was something that inspired us and led to many more papers of research. So how do we work with these within this tiled lattice? And that's where we get aggregates. So an aggregate of level 0 is a single hexagon. There's nothing too fancy there, we're just dealing with that. We then move on to the level 1 aggregate, which is going to be a hexagon and hexagons surrounding all the neighbors. And they're going to be numbered 1, 3, 2, 6, 4, 5, and that's because of the dimension vectors. We have 0, 0, 1 pointing this way, going down would be 0, 1, 0, and then pointing to the left, or to the right there for you guys would be 1, 0, 0, and then the rest are the combinations of those vectors, which give us that addressing system. And then we would move on. The level 2 aggregate would be the level 1 aggregate, which is marked out in red, surrounded by 6 of the level 1 aggregates. And then we move on to, for example, level 3 aggregate, and that would be 6 of the level 2 aggregates surrounding the level 1 aggregate. And the number, or the addressing system stays the same. The paper that originally inspired this was called, it was the isomorphism between the A* and lattice and the p-adic integers. The p-adic integers are really amazing. Dan Rowe helped me understand them a lot more than I really did, but essentially they're, actually I'll go to it. They're integers in Z mod 7Z, which are formed through a combination of primes. And it's really cool. There's a little more about that in my paper, but I won't go too deep into that. So to address these, as you saw, you notice we had the numbers. There's 300 there, 301, 303. It stays the same throughout each aggregate. And that's called the canonical address. So the canonical address is simply a lookup address within Z mod 7Z, so it's just a number mod 7. For those of you who don't know what mod means, it means that it's the remainder when you divide by 7. So you only go 0 through 6 for the numbering system. We can also convert that into a standard address, which is the set of vectors where each digit of the canonical address is written in binary. So for the example here, we have 342, represented as 110, 001, which is actually wrong. No, that's right, and 010, yep, 342. So this helps a lot because a lot of the translations we do are with matrices. So if we're able to convert the address into a set of vectors, we're able to apply matrix operations to them. Which brings us to the B matrix. The B matrix is an n plus 1 by n plus 1 matrix that takes this form. So I put the example of B2 there. And this is used for address lookup. So we're given an address, and it's able to find a vector that relates to that address. And so I'll skip over to the example. So to find that, we have x equals the vector t0 through tk minus 1. That's the standard address that we got, which is that set of vectors. We multiply b by that, b squared, b to the k minus 1. And then I programmed that. As you can see, I created my own matrix class in Java to achieve that, and I set up the matrix class so each matrix returns, each matrix operations returns a new matrix so you can span them. And so what this does is, like I said, it'll give you a vector. So example, if we put in 362, it would give you a vector of 1 times x naught, or v naught, plus 3 times, or plus 7 times v1, minus 3 times v2. And we can use that vector then to translate into other coordinate systems. And that's kind of the part where I got stuck there, was this mapping between coordinate systems. So I'd done all this research, I'd started implementing it, I have the code for it, but we couldn't, I was having a lot of trouble mapping from this special aggregate system into them being able to draw and do operations within like a real number system or an integer plane. So to address that, because I was making a GUI based off of these nonlinear dynamics, I introduced Square World. So Square World is the name of my solution to this problem, that I was having trouble with the aggregates, but have something that I could build the GUI off of, and then when I finally figure out this special aggregate system, I can easily just swap it out because the world would have the same methods and be easily able to translate between the two. So Square World is addressed like you'd kind of expect like a normal hex grid to be addressed. You have the top row of x's is 0, 0, 1, 1, 2, 2 for each of the columns, and then on the bottom there, each level is a new x value. So 0, 0 is that top left corner, but 1, 3 is that yellow highlighted square, or hexagon. So now we can get into the GUI, which I built on top of this, and I'll kind of explain what I did for that. So to create the GUI, I ended up going with JavaFX. JavaFX is the new version, not new version, it's meant to eventually replace Java Swing. It follows Swing's same architecture where it has a model view controller architecture. One thing that I found really beneficial, I switched to it originally because it has vector drawing. So I was able to, instead of using Swing's pixel drawing, I was able to actually draw vectors and made zooming in and moving around a lot easier, and it looked a lot nicer once I had done it. So once I set up this GUI, using a model view controller architecture where, of course, we interact with the GUI, the controller then updates the model, and then the GUI then will display the new updated model. And I use the observer pattern for that. So when things are updated, it just basically sends a message all the way through. So if we change a hex, it sends a message all the way up to the GUI that it needs to redraw, and it represents that hex as a different color or however we did that. And I also used the visitor pattern for the drawing where I visited the world, which then visited all the hexagons within the world, and then it would draw them separately, so that way all the drawing was handled outside of the actual hexagon class. And then I'm going to go into a demo. Are there any just general questions in what I've presented? I know it's pretty dense and a lot of stuff, but all right.
Is the 0, 0, 0 tile a maximal ideal?
By the way, enumerating the hexagonal tessellation was a programming contest problem back in the 90s.
Oh, really? Sorry. Okay, so here is the GUI that I created to be able to model this. You're able to move around using the arrow keys on the tile, and then you can zoom in and out on there so you can focus on specific things. I'll go over exactly what each of these do, but you notice we can add attractors, and we can set that attractor to be a repeller if we choose to. I'll explain what each of these special things are. We can add vehicles with start and end hexes so they can run the simulations along this plane, and that's something I did forget to point out with the Brightenberg vehicles. So traditionally a Brightenberg vehicle would simply just focus on a light source. It would be free to move around the space until it follows it. While I was looking at this, I wanted to mix in some pathfinding with it, because that way if you have a goal, or a start and a goal, and there's some attractor here, how then would it interact with this area around it? So that's what I went with that. We can run the vehicles and then reset the map to this default map. We also are able to save an image, and that shows whatever is actually in this canvas here, so you can zoom in on specific points and save that specific image, or zoom out and show the whole thing. You can load a map and also save a map, and I'll go over the text file, or the in file that I created that loads and saves this. So we'll go, for example, with adding attractors. So we have, let's see my examples here. So we have x, we set that to be 2 and 6. Now the power is how strong the attractor is. So the attractor is a mathematical function. I can show it in the code when we get there, but it's a tan or inverse tan function, so that way it can map all the real numbers to a number between -1 and 1, and then we just converted that by adding 1 to it. So all the tiles start out with the default of 1, and then this attractor or repeller function will modify it to be within 0 and then 2, essentially not inclusive.
So can you explain the logic of the Brightburn vehicle? Does it have a face, or does it go to the hex with the biggest number,
So,
or what?
I guess, it's fair. It's more of a pathfinding vehicle than a Breidenberg vehicle. The reason I did the research into Breidenberg vehicles was because it's still, like, it's following the specific attractors and repellers.
So if the vehicle's on, pick a random hex, where does it go next? It goes to the biggest number, the smallest number?
No.
How do you know?
Well, it'll go to, see, we put a goal in there for the end goal. And then it uses A-star pathfinding to calculate a path, and it utilizes the fact that there's the different weights of the hexes to kind of curve around or
Okay.
find the center. So yeah, I'll show an example of that. So we put in the power as 100. We will set this one to, or we won't set this one to be a repeller. And then this propagation slider. So this is how far out we want the attractor or repeller to extend. So first off, it's going to do a log base 2 reduction on the power, so it'll eventually go down to 0, and it'll get one hex and then a set of hexes. But you can also customize that. So if you want a really strong repeller that's only a single hex, you can set that over here. I'll just leave it at 5 because 100 won't be enough to bring the power of 2 down to that. And we add a tractor, and we notice that updates tractors are colored in green. And then I'll quickly go here and add a repeller, which will be 2. And it's the same thing. We're just able to add it like that. So repellers are. So then, yep. Okay. So with the vehicles, what we'll add is the first one we'll do at 0, 16, and we will have it go to 3, 15. And we'll add the vehicle, and we notice the yellow marks where a vehicle is beginning and where a vehicle is currently at. So then what we expect this to do is we expect it to find a way to get to the other side of these 2 attractors and repellers, and most likely it's going to curve around the repeller. And when we run the simulation, we notice that it's true, it didn't go straight through the repeller. It still hit some of the repeller points on the side there. You can see the path represented, but did not go through the whole thing because using A-star pathfinding, that was still the best path to loop around. Something I do want to point out before going further is this up and over is something you're going to notice a lot with this A-star pathfinding that I implemented. Yes, Jeff?
I'm sorry, where's the start point? The start
The start was at
coordinate
0, 16 here,
and the goal?
was at where it is now, 3,
This is okay, I
Yep.
see block, okay.
Yep, and that's the path that it took to get there. Something important to note is, so I started using a zero heuristic in my A-star pathfinding, which a heuristic is the estimation function where how long it thinks it's going to take to get to a certain point, and it's used to just knock off hexes that don't count easier. That a zero heuristic means it's always going to return an ideal path, but it's also the same as Dijkstra's algorithm, so it's not going to be as efficient. I tried utilizing, I talked in my paper, a heuristic which took the distance between the x and the distance between the y, and it doubled the distance between the x because I calculated that. However, I'm now going back and making it a zero heuristic because I noticed it was getting some incorrect paths, because if you have a heuristic that's too great, it's going to return paths that aren't actually optimal. So you will notice that since a lot of these are the same, it will start to go up and down because it values the neighbor starting at the 1 position, 2 position, and going around. So let's try adding another vehicle just to demonstrate again. So this one will be at, I'll start it at 0, 15, and it'll go up through,
Did you mean 115 or
3,
015?
what? Oh, thank you. Sorry, I thought I turned this off. Okay, so,
That was the Batman reference, by the way.
Yeah.
oh, okay.
Commissioner was calling and you hung up on
And I
him.
hung up on him. Yep. I have to use the red phone. And then if I add this vehicle, we notice it starts there because I must not have changed. Oh, that's right. Yep. I was just not looking at the right Y value that I had in my notes. Then if we run the vehicles again, we notice this one jumps up and makes sure it hits that edge of the attractor basin because it's going to be less notes there. So this is cool, but it's not really modeling the nonlinear dynamics yet. So I'm going to show you just a few other of these like utilities, and then I'm going to move into the actual, two demos that I created of hex or vector fields that you've seen before. So I'm going to save this map, which brings up the save map function, and we'll save it as example. And then if we go to open this up, I can just show you the structure of the save file. So it starts off with the number of hexagons in the world and then the number of columns in the world. That's how a square world is created. And then we have 2 numbers on the next line, 2, 2, which is going to be how many attractors or repellers there are and then how many vehicles there are. So then we move on down to the attractors, which is the attractor values, their weight, whether or not they're an attractor. So one is an attractor, negative one is a repeller, and then the number of propagation units if that's required. Okay. And then we move down to the second one, which is the repeller, and then we have the vehicles, which are the XY of the start and the XY of the finish.
See, it's a programming contest problem.
I know, that's when I was writing, I felt like I was making a programming contest, bro. And then so we reset this map, get rid of all our work, we can then load the map, and then this uses a builder pattern, so the builder will take the file and then create the world and then set the world as our current world. It'll be in presentations and then example, and then we see what we saw again. We can run the vehicles and get the same results. It's a little confusing because of the blue overlapping, but you see what's happening here. So now, if you remember right, we saw this vector field earlier on, which described an attractor as the limit point of a function, where all the trajectories focus in on one point and then extend. So just to show how this is representative of that and that we're able to do these kind of dynamical systems, we're going to load a map that I have saved. We're going to go to our first demo. So here we have a strong attractor in the center, and then 3 different vehicles, and each of those vehicles is tasked to go somewhere on the other side on the same, pretty much on the same Y value. It might be 1 or 2 different. When we choose to run the vehicles, we notice they all go in, they converge on the center point, and then extend out from there, which is representative again of that vector field. Yeah, so it's a little confusing. That one right up in the top started there, and then went up, and then went to that top yellow one. The middle one went to the middle yellow one, and then went to the bottom yellow one. Something I would do now is also add a feature to change the color of each path so that we can identify them separately. So that, that matched the thing. The other vector field we use an example of, would be the curving. So let's open that up. There it is. And remember, so here, the thing is, I don't have directional attractors for this. This is simply just, it's any number of directions. So it'll look different, but we're going to set up where we have an attractor surrounded, or a repeller surrounded by an attractor field. So we're going to open this up in the utility. And then, so we have a similar setup to the last one, except it's that red repeller right in the center. And what we expect to see is that they're all going to go to the other side and avoid the center, which they do. So it's similar to that. They're brought into the attractor, and then they're repelled out by the repeller, so they never actually hit that center point. So those were the 2 specific examples of the vector fields I want to demonstrate and show that this could do. It was, for me, very disappointing that I couldn't figure out that little math bit to actually, fully combine the 2. Like, I had some code for the one, and I just couldn't get it to work, but I think it's something that I'm really excited about. I read a lot of papers about it, so that's now kind of one of those things that I want to finish it just to say that I can. So that's that, and then I would move on to if there's any questions about the program. Yes?
Make me an attractor at 1,000, count 1,000. As long as it doesn't crash.
Yeah, it doesn't crash, it just doesn't
Gotcha.
show anything. So. Yes, Jeff?
Matt, could you explain the cost function again?
For the A-star pathfinding, or
Right.
or the attractor function.
Well, if they're the same thing?
In a way, so I guess with cost, do you mean like the estimated when it's calculating the path, or for the attractor, like when it's creating the attractor?
Yeah, I mean the actual cost, not the estimated
Oh, okay.
cost that A-Star's using. I want to know the actual cost at a particular, given a particular initial, you have a particular goal.
Yep.
So every hexagon should have a cost that
Yep.
should factor in attractors and repellers.
It does, yep. So it's a traditional A-star pathfinding algorithm, like so it's 0 heuristics. So it keeps track of each neighbor and will calculate the cost of moving to that neighbor, moving to that neighbor. It propagates out, and then it takes into account the values of the attractors. And then, like you had said, so like when it finally finds the goal, it will find the shortest path to that. Now, if there's ties, which we notice with these spikes where they go up, it would be the same to just isolate or oscillate and go like up, down, up, down, up, down. But because we're going clockwise for choosing which neighbor is being checked, it'll find the first one that's the shortest path, and that's why we see those spikes. So that's something to kind of work on to fix, would be to probably angle it so it's, looking more forward rather than, kind of like curving like that.
You mean right now it breaks ties in a very biased way?
It does, yes, exactly.
And you'd want to change that to break it randomly?
I don't know if randomly would be the right word, but I think, so ideally to break ties, that would be where the heuristic function would come in. Because if we had some function that estimated the distance, it would actually find those upper ones to be greater because they're technically farther away from the goal point, even though the number of hexes is the same. If I produced the heuristic function right, like I said, I did at the time, so.
Okay. So it's a strange thing you're doing here to me. It's because A star is guaranteed to find the optimal path. So that's a global calculation. So, I mean, normally when you think of attractors and things like that,
Yep.
you're creating these vector fields and everything, and then that's a local calculation. So, you imagine a particle following
Yep.
a path and behaving chaotically or maybe going into an orbit around
Right.
things and everything. That's because it's only looking at
At the-
nearby
Yep.
area, right, the neighborhood. But an A star, any agent, like a Bradenberg vehicle that's behaving according to A star, that's a global calculation, so it'll never go into a loop.
Well, that's what I kind of said was one of the differences between this implementation and like the strict just attractors and repellers was kind of an idea was if we could assign goal points that it was following and then watch how it interacts, around these areas, because it would be easy then to just take out the A star part and have it just, look forward and decide which direction to move. It moves forward if it doesn't see anything, and it can curve or go based on the attractors and repellers. But like if we were running a different simulation on it, where example, something had to get to a goal, and we have a model of this field or this state space we have, how will it interact between those is kind of what I was looking at. So
Yeah, that's interesting. I
Can you
think about
show
the
us-
implications of that, but that's very interesting.
I have some code to show too, but
Show us the A-star code.
okay. So there's the A star code.
Not talk.
Okay. I didn't know if you just want to read it. So what it does is it creates an array list of hexagons it's already visited, an array list of open nodes, things that it hasn't checked but are in the realm of the space, and then it adds the current hex, so the one that the vehicle is existing on, and then it calculates, and then we get a hash map of where it came from. So the came from is how we're eventually going to travel back and recreate the path. And then a default hash map is something I can show, but default hash map was I set up so that way if you give it, if it doesn't find what it's looking for, it returns the max integer. So that way, what I did, I used a null object singleton pattern. So if the A star pathfinding hits a null object, it's going to return the largest integer, and then it definitely won't go there because it's going to be way greater than any other space. And then the G-score, that is the actual value of what it is, or the value of between the goal point and where we're starting. So it's, it's going to calculate the smallest goal. And then F-score is if we had the heuristic function, which is, going to be defaulted at 0. So while there are still nodes in the open node set, it's going to take it's going to set the current to be the one with the minimum F-score, which in this case, again, it doesn't really matter because we're dealing with heuristic of 0. If current equals goal, we return the path, and then we can create the path based on, because we have that came from hash map that'll just travel us back. Otherwise, we remove the current from open nodes, we set it to already visited, and then we take all of its neighbors and add them to the open nodes with a specific G-score, which is the G-score of how long it's taken to get there plus its weight. So if the weight was 1 and it's taken 5, it's taken a path of 5 weight to get there, that would be 6. And that's stored in the G-score array list that I talked about. And then it puts came from, neighbor current, and then it puts the G-score and puts the F-score, which again is just the heuristic of 0. So.
Why Java?
So we can talk about, I chose Java for a few reasons. It offers a lot of pre-built classes. Well, it's object-oriented, first of all, and I really wanted to focus on creating a good object-oriented program. I had a little bit of experience with Java from previous things, and it also offered a lot of built-in GUI classes, eventually with this JavaFX vector drawing, and some other data structures I was used to working with and that I wanted to implement. And also it helped out that the job I'm going to be going to uses a lot of Java, so it was a good way to get brushed up on that ahead of time. So.
Here's a question. Would your code break if you changed your already visited array list to a hash set? And what would be the consequence in the code?
I change it to a hash set. It would probably, it shouldn't break, and it would actually improve, calculations, because it would just find that it would be a direct lookup of the hash set. So that's a good point, and I can do that.
Are we in the general questions or
Go
just
for it.
code?
General, I have more code I can show, but I'm also open for general questions. So.
Okay, so I have two. So a while back, sarcastic something was a maximal ideal,
Yep.
which implies that there's a little algebra somewhere. There's a ring structure. What is it?
So that was one of the papers that I had read with the ring structure, and I'm not too well-versed, to be honest, so there's more in my paper, but it's the EGBT integers would be the ring, and it's isomorphic with the p-adic integers is where it comes from. So this EGBT is the address, it is the set of addresses within this, and that would create a ring, actually, because it's bounded through addition and multiplication. You could do the vector calculations through that. So.
Okay, interesting. And the second is more of a request. I noticed there's some people in the room I don't recognize.
Okay.
Could you introduce them, or the hired actors?
I just was like, I hope people show up to support Noah. So we'll start with the very back. In the white shirt there, that's my sister, Nicole. And then in the plaid, that's my fiance, Abby. We're getting married this July, so that's really exciting. And then my mom is there in the stripes. And then my great aunt Mary is over there. And then Jeff Horn. And then that's those are Abby's parents, Tom and Ann. And then you should know Adam Call. And then in this front row on the couch is Megan O'Brien, Hattie Foley, and Aubrey Call, some of my friends from school.
Hey.
And then I was getting over there. And then that's my dad who's helping videotape. So thank you.
They had a fight earlier.
Could you show us some of the observer codes? Since
Yep.
I asked that last time. We had some.
So I'll just quick, because I was kind of going into the controller. So this is what the it looks like for creating the GUI. So it uses an XML file. JavaFX uses an XML file similar to if you've programmed an Android or something like that for creating lists. And then that's all controlled through a controller. And something I really liked was that you can put in the methods for like the buttons here. So you have on action, you hashtag handle add attractor action. And we move on to the draw controller. And if you go up here, you actually are able to just directly say at fxml and then what it does. So for example, for the save, we're able to open up, set the save config file, find the selected file, open it. As for the observer pattern, I'm trying to think of the best way to show that. Do you mind if I quickly show? I'll show the visitor pattern really quickly first because
Okay,
that's already
sure.
open now. I'll find the observer. So here's like, for example, the save visitor. So like I said, we'll start by visiting the square world. And then it writes everything it needs to. Then it visits all the attractors and then visits all the vehicles. And then they on their own are able to reference themselves and print out what they're supposed to. And then the builder class simply takes that and would open it back up and parses it through. So we'll get rid of those. Sorry, observer pattern. It's all over. I just have to find like a good spot to.
Yeah, like a hex or
Yeah. Well, here's so for example, here's the update function within the controller.
right.
So it receives an update and it address. And then if we open up a hexagon. It's also my first time using IntelliJ for this, and it's really handy, but I was very unused to it. So let's go to hexagon. Where's? Well, I can tell you I have it. It's blank.
Can you do senders?
I guess it wasn't. It's odd. I know I ran into a few issues where the world was getting initialized ahead of time, so I might have taken out of the hexagon. Let's see if we changed. Okay,
There
so
we
for
go.
example, when it solves the paths, all it has to do with Java, the observer pattern, is it sets the item is changed, and then it notifies observers. And when we create the square world, or when we create the GUI, it sets the world, or the GUI as an observer of the control of the GUI as an observer of the world.
Okay.
So an update.
Did you make the FXML file by hand, or is there a drawing editor?
There is a drawing editor. I made that by hand. That's how I've done it for Android too before, and it just felt more comfortable for me to just go in and play with the values and work it through hand. So, yes.
So do your Brakenberg vehicles ever behave like, you know, the original Brakenberg vehicles? Can you turn off the A-star?
That's something I could easily add, but I didn't do that, no. So I researched Brainerd vehicles, but I didn't set it up to do it. But there is, I mean, it would be pretty easy to add a method to say run vehicle, and all it does is search, you know, its direct space, and then would be able to interact with.
Yeah, you get much different dynamics.
And that, it would be really something to compare the two and see how it
Yeah,
changes.
the A-star dynamics are gonna be, it doesn't matter what the heuristic function is, right? It's always gonna give you the same vector field,
Right, yep, it will always give the same vector fields.
and it will be much less nonlinear, whatever that means, than if you had an actual Brakenberg vehicle. So I was just wondering if you had a way to explore other, I mean, what are you interested in the nonlinear dynamics, which you said you're interested in? What kind of nonlinear dynamics?
No, I guess that's a very good point, and I guess you know, so you have the Brainerd vehicles, which which are like would be like a true nonlinear dynamic where it would actually like navigate around some sort of space. If I were by having the A-star on, I guess it's more I already have the vector field set up in a way, and I'd be planting something and watching the trajectory, but hoping it gets somewhere. You know, so like Brainerd vehicle would be I place it in and it would follow a trajectory based on the vector field. With these, I'm saying like it has to get somewhere. I don't know, it could be a creature for a simulation or something. So how does it interact within this vector field? And it still does follow the vector field, but it's different, like you said. You don't get as much nonlinearity in there. So.
Yeah, it's like a minimum nonlinearity.
Yeah, no, that's
But that's interesting. That's really interesting to see how nonlinear can be as a function of the attractors and repellers.
Yeah.
Like, you know, where they are, how many there are, and all that. So, sorry, I'm just talking out loud.
No, I learned about Brainerd vehicles in your class, so go ahead. Grill me.
Why don't
I
you,
remember.
why don't you tell us about points?
Okay. It's okay to just do it with just like the faculty. I don't know, it feels weird to just talk. I did well, but is it okay if like you send people out now? Okay.
You can do this. End however you want to end it. Tell us how
All right.
wonderful you are. Tell us how cool your thing is.
I really enjoyed working on this. It took a lot of time, and you know, I did put a lot of effort into it. There were some things that came, or not things that came. What is it? The word. I was going to end on, so it's like really great to end on, and now I'm just blanking. But I really enjoyed working on this. It's really cool that I got to combine my math and my computer science in a way, you know, looking at abstract algebra, some analysis there with the mapping of the functions, and also putting into a program, and then a program that can be used later on because it's a GUI that's built onto all these frameworks that I created. So, and it's, oh, that's what I was going to say. It's some of the best code that I've ever written because I actually like stayed true to patterns and to principles that I'd set up in the beginning and followed through with those to the end. So I was very happy with that. And it ended up being around 1,800 lines of code in the end. So.
Okay. Thank you.
All right. Thank you, guys.
You stay. Get out. You can stay if you want.